my fellow assassins, to another episode of the Dark Assassins Podcast, the show that dives deep into not just technology, but the concepts, software, and procedures behind it all, and explains it so simply that even your grandma can understand it. As always, I'm your host, the Dark Assassin. Now, before we get into this week's episode, I did just want to give a shout out to the listener or fellow assassin that requested this episode topic. And just as a PSA, if you have any topics, ideas, for episodes, you can, if you're on YouTube, you can always leave a comment down below and I will see that. And if it's good like this one, I'll definitely be sure to include it in an episode. Or if you're listening on podcast, you can shoot me an email at contact@darkassassinsinc.com. And as always, the link for that is down in the show notes below. But with that out of the way, when it comes to CPUs and GPUs, probably one of the most common questions I hear people ask when it comes to this is they see how powerful GPUs are, and they ask the question, well, if GPUs are so powerful, why don't we use them in place of CPUs and do all of our computing on them? Because obviously, they're running these massive AI models. They power, graphics in our video games, and they do so much so well. Why don't we use them instead of CPUs? Because if you try to do these kinds of tasks just on a CPU, your performance is going to be significantly worse. So if the CPUs are just so much worse, why are we still using them? And the TLDR here is GPUs aren't designed for general purpose computing like CPUs are. CPUs are specifically designed for wide varieties of software to run on them, operating systems and all the software that runs on top of them. Whereas GPUs are basically significantly designed for one specific purpose. But before we get way too far ahead of ourselves, because we're kind of already delving into the topic there, let's start with our trivia question for the week. So this week's trivia question is Skype, which Microsoft just discontinued this month, RIP. When was it initially released? So when was Skype initially released? And that is your trivia question for the week. Now, before we get into the cybersecurity tip, one thing I did want to give a quick call out to was that that string copy video that we posted on the YouTube channel kind of popped off a little bit, at least for our standards. Now, in terms of like YouTube as a whole, it's basically nothing. But for us, kind of blew our view total for any video out by a mile. Like it did pretty well. So if you haven't checked that out and you're interested in kind of how stir copy can be exploited via buffer overflows and how to remedy it, we kind of touch on that in the video. So if you're interested, you can go ahead and watch that. But kind of on the similar topic of buffer overflows, let's get into this week's cybersecurity tip. This week's cybersecurity tip is to not fall for the trap of signing up or signing into accounts with existing accounts like social media accounts, Google, etc. Now, if you don't care about your privacy or security, I guess by all means, go ahead and do that. But the reason I say if you don't care about either of those things is on the privacy front, by the fact of you linking whatever it happens to be, whether that's your Google account or a social media account like Facebook or Twitter or I guess X or whatever, you're inherently letting that social media account or Google know that you are linking your account with them to this other service, which is just another data point for them to use however they please. And that's just at the surface level. That's like not even considering if basically if there's any possibility that that is all that these companies will get from you by just signing up to a service. So let's say you were trying to, I don't know, grocery store or something. Say the grocery store you go to, they have like a sign in with Google option or something. Google now knows that you shop at that grocery store. Now, to the extent that that grocery store shares information with Google in regards to like purchasing habits and all that kind of stuff, kind of TBD. We don't exactly know because it's not like any of these solutions are open source. So yeah, I mean, I guess if you delved into like the APIs for how these processes are called, like, signing in with these other accounts, you might be able to glean some kind of information as to potentially what kind of sharing might go on there. Back in the day, like 4 years, I don't remember, it's been a while, when I graduated from my undergraduate degree, one of the classes that I unfortunately had to take was a basically a web development class. And the TLDR of why I took that class was the school I went to was pretty small, and I was getting a minor in cybersecurity. And as such, the only other, basically, in order to graduate, I had to take whatever other computer science elective was offered because I was already taking the cybersecurity electives. So I was forced into taking a web dev class because that was the only one available, and I wanted to graduate on time. So one of the things that I had to do was kind of implement this with the API to essentially allow you to sign in with like other accounts. Personally, I don't remember all of the ones that I supported. I think it was GitHub was one of them. I think Google was another one, and I think there was a third one. I don't remember which one it was. But the point is, from what I remember, pretty much all I did was had the button there. It would kind of take you to the third party's website. You'd log in, and then all it would do was basically call to get like what your name slash username was to basically welcome you, and that was basically it. So aside from that, whatever happens under the hood as far as linking goes, your guess is as good as mine, because that's pretty much all the looking into it that I did, because that's basically all the interest that I had in it, which is to say not much. But suffice it to say, there's still that initial linking process that goes, which for sure gives whoever, whichever social media account you're linking to, a heads up that you're linking to the service, which can then give them more information to profile you and then sell you ads or sell your data to third parties for who knows what. But that's the privacy aspect. Then there comes the security aspect, which if you don't care about the privacy aspect, that's, I guess that's one thing, because there are people nowadays where that's basically all of they've known their entire life is basically having no privacy online. But the security aspect is where you really should be paying attention. Because if, say, you log into one of these accounts with your Google account and your Google account gets hacked, well, guess what? Any account that you linked with sign in with Google is now compromised as well, because they can just sign in with Google, and because they already have access to your Google account, they can just freely sign in and you're basically toast. And that's kind of one of the other, I guess, issues you could say with kind of having all of your stuff related to your security in one spot. Like, for instance, going back to the Google example, like if you use Google for your email, you use Google for your like your two-factor codes and all that stuff. If your Google account gets compromised, you are absolutely 100% cooked. If you, say, had a separate like authenticator aside from Google that was completely separate from your Google account, yeah, if someone hacks into your Google account, you're going to have a very, very, very bad day, and you might have some of your accounts get compromised. But if you have two-factor authentication with a authenticator app that isn't Google, you at least have a little bit of saving grace there, because even if they do try to send the "I forgot my password, let me reset it" link, yeah, they're going to get that link and go to it, but they're probably going to almost in most cases, I would at least hope. I guess it depends on the site itself. But they're going to prompt you for like a two-factor code to basically, just another level of insurance. And if you don't have it through Google and it's through some other authenticator app, then that's at least another level of protection that you have. So yeah, that is kind of the security aspect of why you shouldn't sign in with any one of those like options. Now, I know it is very convenient to do so because at the same time, it's another password that you don't have to remember. But as we touched on, that's really not an excuse anymore. There are plenty of password managers that are fantastic. You can even self host your own. So there's really no excuse for saying, oh, I can't remember passwords, so I'm just either going to use weak passwords, reuse passwords, or just sign in with some other account so I don't have to remember passwords, because it's easier now than ever to not have to worry about remembering passwords because password managers exist and how good and robust they are. So yeah, don't use sign in with X site if you care at all about your privacy or security, and that is your cybersecurity tip for the week. Moving right along, let's get into what nerdy stuff have I been up to this week. So last week we talked about how I implemented kind of the algorithm and the underlying code to generate random encounters. Well, this week I got the entire encounter table system built. So this is for not only the Pokemon, but also I just threw items in there too, just because I figured that might be something that might be needed down the line, since from kind of recollecting, there are instances where there is somewhat of a random item generation thing. Like the most notable one that comes to mind off the bat is the pickup ability. So if you haven't played Pokemon before, essentially what the pickup ability is it's an out of battle ability that essentially, once a battle ends, there's like a certain percent chance that your Pokemon could pick up an item, and what item they pick up is kind of based on a couple of different factors. But there's basically a table that has various percentages, like I said, based on factors like I think the level factors into it. But essentially, there's like different weights for the different items that you could potentially pick up. So that's one of the reasons why I kind of threw items in there as well. But it's just a single encounter table, and then there's like different encounter entries, and then you can basically define in the encounter table if it's an encounter table for Pokemon or if it's an encounter table for items. So basically, kind of added that dual functionality in there, basically to not make the same thing twice. So that was quite nice, and the one of the ways I was able to do that was essentially through some inheritance goodness. Basically, create a base encounter entry class, and then have two inherited classes, one with the Pokemon and one with the item. So that way you can just create the same encounter table and then just set a flag inside the encounter table, basically just letting what type of encounter table this is for. And then when you go through the code of like generating encounters and getting encounter entries back, you kind of can piece together, what you're dealing with. So that was a big win. One of the funny things was, though, when I was writing my test cases for it, um, for whatever reason, the equals equals check was failing. And thankfully, this wasn't one of those instances where I made a dumb mistake and then banged my head against the wall for a few hours in order to figure it out. This time it only took me about 5 minutes to figure out, which I was very thankful for. But like I alluded to, the mistake was a very stupid one. So like I said, the encounter table uses encounter entries. It basically has an array of encounter entries, and those are basically pointers to individual encounter entries. So my genius self was comparing pointers to pointers. So I had written all the code out to compare entries to entries, right? So I wrote the equals equals overload operator for an entry. So basically comparing the ID of it, comparing the likelihood of it, and then some of the other factors involved. So that was all working, and I knew that should work. but of course it wasn't working. And yeah, it makes sense if you're comparing the address of one entity with the address of a completely different entity. Of course, the addresses are going to be different, and if the addresses are the same, well, they're just pointing to the same thing. So thankfully, that was a very quick fix. I managed to find that one rather quickly. But yeah, so definitely a big rookie mistake on my part. But I am very thankful that it didn't take me very long to get sorted. And then the other thing I did was something that was, in all honesty, worthless, but definitely makes the development a lot more streamlined and easy, I would say. So this has to deal with the test case menu. So this was another instance where it was one of those bad coding habits that we talked about in like a previous episode, where you essentially have an if statement that just grows and grows and grows and grows and grows and gets like unmanageable. That's essentially what was happening here. Now, granted, I was using a switch statement rather than an if statement, but the same principle still applies. It was getting pretty unruly. And the other part that was also very annoying was I basically had essentially two of these. I was manually entering the table entries, and then I was manually entering the switch statement, for all of the various potential test cases that you could run based on what number you inputted. Now, one of the submenus I actually did slightly smarter, where I was basically creating a counter and then basically incrementing the counter after every test case, so it would always auto increment, so I wouldn't have to change that. But I still would have to like reorder things. And but the switch statement, if you like reordered something, you'd basically have to change all the numbers below it, which was a royal pain in the butt. So I decided to essentially overhaul how that entire system works, and I noticed while I was overhauling this that there was some redundancy in the code of how these functions were being called. So I basically abstracted that out into I just created separate not class, separate file specifically for menu related things, to basically kind of abstract that away and just call that one function and give it the proper parameters. So the things like running tests and printing the menus, I basically just created two separate functions for those because those were very much the same, copied across multiple files. So this is a fantastic example of tech debt that you didn't necessarily intend on making, because originally, if you have like say a few test cases and you have a switch statement to, switch based on the input number, it's not that big of a deal. But then when you start getting to the point where I don't remember how many test cases I'm at, but it's ballpark like 35, 40 at least. So 35 or 40, you can imagine how unruly that kind of a switch statement would be. Now granted, it was divided up amongst a couple different switch statements, but still each switch statement had probably 10 or more items in it, and then the menus also had 10 or more items. So anytime I would want to reorganize something, I basically tried to avoid that as much as possible, just to reduce the amount of minor code changes I'd have to make in like the kind of organization of things. It was very annoying. So instead, what I ended up coming up with was which ironically, as soon as I came up with the solution, I was like, man, I should change this. But the solution is without a doubt a heck of a lot better. So how it currently stands now is there is two different arrays. One is for the name of the test case, and the other is essentially a function pointer pointing to the test case itself. So essentially, what happens now is there will be a loop that loops through the string of test case names and then prints them out. It actually does some print formatting this time, so it actually like makes multiple columns, which is very nice because once you get to the point where you have a lot of test cases, it kind of extends and extends and extends, and it gets to the point where you kind of have to scroll to see them all. So having multiple columns allows you to fit more test cases, which is nice. So added that. So it basically just takes in the array of test case names and then prints them out rather than having a different print for every single test case. So that is very nice and a lot more reusable. And then on the flip side, the one with the function pointers, it basically just checks to see if the number you inpointed is within the range of the array, basically within the limits, and then run the test case that was selected, and bada bing, bada boom, you got your test cases running without a massive switch statement. So overall, massive improvements to how the test cases are laid out, and it makes it so much easier whenever I want to add a new one, because literally all I have to do is I can put it wherever I want in the array, and I don't have to worry about the numbers being messed up in both the switch statement and the menu, because all that's handled dynamically now. So it is fantastic. Now, I mentioned that as soon as I came up with the solution, I thought of a better one. And it's kind of a nitpick. It's a minor thing, especially considering, like I said at the beginning of talking about this, that this has absolutely no impact on the final product at all. Because if slash when this game ever gets to the point where I think it can be shippable, the test cases will never be seen by anyone aside from someone that maybe wants to develop for it. I don't know. But so the thing of it was, I was like, okay, this is great, but knowing me, I would inevitably run into the situation where I update, say, the function pointers and like kind of reordered them, but I didn't reorder the names of of the actual functions themselves, like in the menu array, and there would be a disconnect there, and I would be wondering why the tests aren't running the tests that I think they should be running. Um, so basically, just to kind of get rid of that entirely, the new plan I'm thinking about is either to use like a hash map or an unordered map or some kind of map, or just create like an array of pairs or something like that, just so the name of the test case and the test case itself are always together rather than in two separate arrays, since that way theoretically you could still mess things up, like you forget to update, say, like if you're using a pair, you forget to update, the first value, but you update the second one. Or in the case of a map, you don't update the key but you update the value, so you could still run into the same error, but it's all in the same, I guess, data structure, if you will. So that's kind of what the new process I'm thinking of. Of course, I haven't gotten around to doing that yet, because I'm still talking about this in a theoretical sense. But that is kind of the next thing that I'm kind of thinking about, potentially making updates to this menu system. But yeah, those are the updates. So the encounter table one was obviously the big one, but the menu one was definitely a very big quality of life improvement. Removed some technical debt, and definitely was a much needed refactor. So, with that, I think we should get into talking about CPUs versus GPUs, and specifically kind of the architectures and how they differ. So, I guess first off, we've been talking about CPUs and GPUs, but in case you don't know what either of those acronyms stand for, CPU stands for the Central Processing Unit, and GPU stands for graphics processing unit. So, when it comes to the CPU is essentially the brains of your computer. It handles calculations, executes instructions, manages data. Basically, anything related to computing needs, the CPU can do. Now, it might not necessarily be the best at doing it, but if it can be written in code, the CPU can execute it. GPUs, on the other hand, are more specialized chips, and they're mainly designed for graphics, rendering, and compute tasks rather than kind of general purpose computing tasks. And we'll get into a little more specifics of what that means. But we've talked on the podcast before about the importance of hardware accelerated chips, and that's essentially all of what a GPU is. One thing you'll kind of hear thrown around when you're talking about hardware specific or hardware accelerated chips is this idea of ASICs, or application specific integrated circuits, and GPUs fall into this category. Now, what ASICs are, if that name kind of sounds familiar, One of the reasons why it might be familiar to you is because of cryptocurrency and crypto mining. Now, crypto mining kind of made ASICs very, I guess, mainstream because that was basically the only way that you could mine certain cryptocurrencies like Bitcoin and then eventually Ethereum, I think, kind of got to that point as well. But the point of ASIC miners was literally that's all those computers would do. They were only good at one thing and one thing only, and that was basically running the hash algorithms needed to compute these hashes for cryptocurrencies to earn the block rewards. Um, but if you had them do anything else, like you couldn't run an operating system on them, you couldn't basically do anything else. They had one job and one job only. So if you weren't using them for cryptocurrency mining, they essentially turned into a very expensive paperweight. But kind of getting back to GPUs, um, like the thing with GPUs and kind of like the idea of hardware accelerated chips is a lot of modern CPUs and kind of I guess processors in general are having like specific hardware accelerators built into them. And Apple's processors are a fantastic example of this with Apple Silicon. Apple Silicon has, media encoders in them, it has the neural engine in them, and all of these different components are hardware specific elements designed only to do that one task. Now, sure, it has its own CPU cores, but it also has these specific in like hardware chips on it on the package specifically for those one tasks. And other examples is like Intel QuickSync is another example of specific hardware accelerators built into like a CPU. And in the case of Apple's media encoders and Intel QuickSync, these are specifically designed for encoding and decoding media formats. Now, you can absolutely encode and decode media formats on a CPU, just, raw software encoding or decoding, but your CPU is going to get very hot, your fan is going to scream, and it's not going to be very fast. But if you use, say, a hardware accelerated encoder, it's going to be very quick. And GPUs are also very good at doing these kinds of media encoding tasks as well. But if you don't believe me that your CPU will scream, sweat, and be very loud and very slow, I encourage you to say open up a program like Handbrake and try to software encode a media file and then use the same media file, do it again but with hardware accelerated encoding, and you will see it is a completely different world in terms of power draw, in terms of noise, in terms of heat output, and in terms of performance and speed and how quickly that file gets encoded. So that's kind of like a brief kind of intro to them. So, kind of getting into the similarities between CPUs and GPUs because this is going to be quite quick. Um, CPUs and GPUs both execute instructions. I think that's fairly obvious. But you can write code to run specifically on a CPU, and you can run code to specifically run on a GPU. Now, the code that you write is going to be slightly different for each of those use cases, but the point still stands. You can write code to execute on both chips. The next one is they both perform calculations. I think this one's also kind of self explanatory. Anything that you do on the CPU, I mean, there's a lot of different things that you can do, like any kind of your basic intro to programming, any kind of programming you do, any kind of calculations you are performing in your code is running on the CPU. Um, there are now if you can definitely do calculations on the GPU too, but you kind of have to use specific libraries or programming languages, which technically, I guess CUDA is its own programming language, but it's essentially just C++ with like the CUDA framework slash library slash SDK. So I don't know. We had a debate a while ago about at what point do like frameworks and software development kits kind of become their own programming language, and I think that's kind of a good example, kind of where CUDA fits into that. But regardless, yeah, GPUs and CPUs both perform calculations, and they both rely on memory speed, both in capacity and bandwidth, in order for maximum performance. So obviously, the faster that your CPU or GPU can access memory, the better it's going to perform because it can access that memory quicker, and can perform the calculations it needs. It doesn't have to wait on those memory retrievals. And they both have like dynamically adjustable clock speeds. This is very evident if you kind of view kind of the activity monitors on the various operating systems. You can kind of see like the clock speeds that your chip's running at. So both of them have the ability to basically ramp up, and kind of in the case of like CPUs, it's usually called like turbo boosting, or like its turbo frequency, where it can, for short bursts, like, ramp up really quickly and, to perform and the various tasks it needs to perform very quickly. And then when it's not as you being utilized as much, it can like ramp down the clock cycles in order to conserve power and whatnot. And both the CPU and GPUs can both do that. So that's basically the similarities. Now getting into the differences. One of the most notable differences between CPUs and GPUs is the core count. Now, the average desktop CPU, at least modern desktop CPU, if you wanted to look at, say, back in like 10 years ago or so, like the mid 2010s, 4 cores and 8 threads was basically the bread and butter because that's all Intel did because they had no competition. So they basically just sat on their hands and was like, 4 cores, 8 threads, it's good enough. Nowadays, though, since there's more competition from the likes of AMD and Apple with their Apple Silicon processors, and Qualcomm's kind of coming onto the scene as well with their ARM based chips, there's a lot more competition, so there has to be, more performance edges, generation over generation. So nowadays, it's fairly common to see desktop chips with 8, 12, maybe even 16 cores. And then, of course, you can get to like the higher end, like workstation chips that might have like maybe 32 or 64 cores. And then, of course, you get into the server world and it's like sky's the limit essentially. It's like I don't remember what the latest numbers are, but there have been CPUs I think with 100 and I want to say maybe 192 cores. I know 128 for sure. I think 192 might be one. There might even be a 256. I don't know. They're pretty bonkers. But that's of course in the server world. Your average desktop isn't going to be using one of those very expensive chips. Now, in contrast, you have GPUs. Now, just to give you an example, the RTX 4070, which I know is technically an older generation card at this point since the 5000 series is out now, but the RTX 4070 has 5,888 cores. So, yeah, just a couple more than the CPU. Um, but anyway, it's pretty easy to see why someone could see this massive difference in core counts and think, well, the GPUs obviously have way more cores. They're very, very powerful. Why don't we just do everything on them? And that's kind of where we started this episode off with. And, it's not, a bad question on the surface because if you don't really understand that GPUs are designed specifically for essentially one task, which is like computational stuff and like graphics type tasks and not general purpose computing, it's very easy to see, ask that question, and it's valid. Why don't we just do all of our, general computing needs on GPU? Because it obviously has way more cores, and more cores means you can do a lot things faster and parallel. Than you can on, say, in a desktop. And while typically speaking, more cores means, well, on the CPU side, and I guess also GPU, it's generally understood that more cores equals better performance. Now, there are tons and tons of gotchas and caveats, things from making sure that the CPUs are from the same generation, that the one they're using the same type of core layout. There's the same architecture, same core layouts, same kind of nanometer process, yada yada yada. There's a ton of gotchas, but generally speaking, two CPUs from the same generation, generally the one with more cores will have better performance. Now, that's not, of course, 100% always going to be the case, but generally speaking, that's a good rule of thumb to follow. Of course, manufacturers, an AMD CPU with, say, 8 cores is going to have a different performance than an Intel CPU with 8 cores. We understand that. But the point is, generally, the more cores, the better performance you're going to see. So, but when it comes to, the idea of cores, there's a reason why GPUs can have so many cores in basically the same size die package as a CPU. And the reason for that is GPUs like individual core on a GPU is much simpler than a CPU core, because as we touched on, CPUs are designed for general purpose computing. So there's a lot more complexity and transistors in each individual core in order to handle this general purpose nature of a CPU. So CPU cores are just way more complex with way more transistors and more specialized circuits in order to handle that wide range of tasks that a CPU is required to handle. Where in contrast, the GPU, it's more specialized, so it doesn't need all that extra silicon and all those extra transistors and logic gates and all that good stuff that the CPU needs, because the GPU basically only has one purpose. So because of that, and because GPUs are so much more specialized, their cores and transistor layouts they're much simpler and much smaller, which allows you to cram a lot more of them in the same amount of space compared to the CPU. So, one way that you can kind of think about this is think of it like a pocket knife versus a multi tool. The multi tool is like your CPU. The multi tool can basically do whatever you need. Is it going to be the best at it? No, not even close. Is it going to be the best saw? No, not even close. Is it going to be the best knife? No, probably not. Is it going to be the best pair of pliers? Probably not either. So it's not necessarily the best at anything, but it can basically do anything. And that's kind of the benefit of a CPU. Contrast that to a pocket knife. It has a single purpose and that is being a knife. Now, when you compare the size of, a typical pocket knife versus a typical multi-tool, the multi-tool is going to be significantly bigger and more bulky than a pocket knife is. The pocket knife is going to be a lot slimmer, it's going to be a lot sleeker, and it's going to be a lot smaller both in terms of size and weight compared to the multi-tool. And the same thing basically applies to CPU and GPU cores, where the GPU core is more akin to the pocket knife and the CPU core is more akin to the multi-tool. So, of course, the CPU can do a much wider array of tasks like the multi-tool can, where the GPU is more specialized and more specific, thus allowing it to be a lot more smaller and compact. So hopefully that kind of helps kind of clarify this, why you can fit so many more CPU cores, or so many more CPU cores. Why you can fit so many more cores on a GPU compared to a CPU, because the simplicity of it. Now, the next kind of big difference between CPUs and GPUs is the idea of parallelism. Now, you can absolutely achieve parallelism, or essentially the idea of running things concurrently or at the same time on a CPU, but CPUs are typically more designed for sequential tasks. So if you've ever written code before, you know that it follows a very sequential order of things. First, you do this, then you do this, then you do this. Maybe you have a branch there where if this is true, you do this. Otherwise, you do that. But essentially, you're going down step by step in sequence in order of doing tasks. GPUs, on the other hand, are very different. The whole point of GPUs is doing things in parallel at the same time. So, kind of writing algorithms for GPUs is generally a little more complex because you have to take into account, the parallel nature of basically running a ton of different threads all at the same time. Which, sure, there is, of course, there is multi-threading in CPU, like your typical, programming languages, but it's generally not quite as complex as the GPU. Now, like I kind of touched on with CPUs, you can absolutely um, write, multi-threaded applications, but it's still because if you look at, say your activity monitor or task manager or whatever, if you click on any individual application, in most of the time nowadays, you'll see that application is using multiple threads, and essentially what that means is, it's having multiple things potentially executing at the same time. And the other benefit of threads too is if you run into an instance during your sequential processing where you hit kind of like a blocker, things like user input or waiting for network traffic or waiting for file IO or things like that, you have other threads that you can continue performing other tasks in the background while you wait for that main thread, so you're not completely blocked. Of course, that's assuming you're actually using a language that can have multiple threads. Now, of course, if you're using some inferior language like JavaScript that cannot handle and support multi-threading, well, then you're basically just stuck to single-threaded performance, which is the joys of what happens when you're using JavaScript. And that's kind of one of the reasons why older computers generally slow down in terms of their web browsing performance, because the entire web these days, whether for good or for not, is basically all JavaScript, and JavaScript is all single threaded. So yeah, if you don't have good single threaded performance and there's a ton of JavaScript all trying to, run at the same time in one thread, you're going to get bogged down. You can't kind of split the tasks up and kind of run in parallel. But JavaScript rant aside, even with multiple threads, instructions are generally still performed in some sort of sequential order, right? Like, in most cases, if you're using like most of the time when people like are dividing up threads, it's kind of, for those types of things, like, things like thread pools, worker queues, that kind of a thing. And you're basically having multiple threads for different queues of work to do, but each one of those, sequences of work to do is generally a long sequence of steps of, if then conditionals, for loops, maybe some while loops and function calls and that kind of thing. It's very sequential, even though you can be performing things in parallel, which is different on a GPU, because typically on like GPU parallel computing, you're talking about things like matrix multiplication or some other kind of just straight up math operation that you can perform in parallel. And that's typically kind of the main difference between the parallelism between the CPU and GPU. So if you've ever written like CUDA code before, which is specific to NVIDIA, one thing that you'll have to manage is the blocks and threads that you want your function to use in order for the GPU to do its parallel calculations. Now you can manually set that, or you can do some ways to basically allocate everything depending on what you're trying to go for. But a fantastic example of this parallelism in action and why the GPU is so good at these kinds of calculations is harkening back to a program that I wrote a couple years, maybe more than a couple years ago. But a few years ago, I wrote a program to essentially take the idea of taking a large number that is the product of two primes and basically factoring out the original prime factors. And kind of the inspiration for this project came from the RSA algorithm. Now, we've talked about RSA in the past, but kind of to put simply, the key generation scheme of RSA partially relies on taking two very, very, very large prime numbers and multiplying them together to get another value, which is essentially your key, or one of your keys. So kind of the idea is, if you can, basically find the prime factors of that very large number, you can then basically break RSA. So that was kind of the idea, just on a much smaller scale. Now, for context, the numbers in RSA are like, I think it's 248 bits and even like 4096 bits. The number I was using was significantly smaller than that, essentially 64 bits. So the numbers that I was approaching was essentially 2 to the 64, or around 18.4 quintillion, which is still a massive number, but compared to the numbers used in RSA, still very, very small. But the point of this exercise was to just demonstrate how the parallel nature of a GPU can really shine in these kinds of like raw compute type scenarios, because basically what you're doing here is you're basically doing math operations in order to find what the prime factors are. And because you can spread that out across all those threads and all those cores to do all that computation in parallel, it's a lot quicker to do it on the GPU compared to the CPU, and the numbers showed that. So in the specific test case I was using, granted, I was using I think I was using 8 cores of a Xeon 2695 V2, I believe. So using 8 cores of that versus the full force of a was it a Tesla P4? I think it was. So a Tesla P4 versus essentially 8 cores of a Xeon from, I think, 2013, 2012, something like that. So essentially what happened was the CPU got absolutely creamed. The CPU, for like the largest numbers, kind of approaching that 18.4 quintillion mark, it took over 2 seconds in order to find the prime factors for one of those numbers. Compare that to the GPU, which took, I think, just over 100 milliseconds. So essentially over 2 seconds versus 100 milliseconds. So the GPU is essentially to run an average score test, which, for the sake of the program, I just had set to 7. It was a very arbitrary number. Essentially, what I did was I picked 7 because I would essentially throw out the lowest score and the fastest score and the slowest score, and then take the average of the ones in the middle to compute the average. So the GPU is able to run through basically the entire test suite that I had in less time than it took the CPU to do one calculation for a single iteration of like the 18.4 quintillion number. So I think I ended up having like, I don't remember how many numbers were in the test cases. I think it was like probably at least um I think it was somewhere in the teens, I want to say. But essentially the GPU was able to run through all of them basically instantly. The program essentially finished instantly, whereas the CPU one, it did the first few very, very quickly, in some cases faster than the GPU, which we'll kind of touch on why that was in a little bit. But then when it got to like the larger numbers, it was like the next one, the next one. It was very slow. Whereas the GPU, it's like starting the GPU test and it's done. All of them, every single one, all 7 tests for every single one, done. So yeah, very, very quick. And that's just, attributing to the parallel nature of the GPU, because GPUs are so good at parallelized math operations and math equations, which is why GPUs are so prevalent in AI, because in training AI models, because essentially that literally is all what AI is under the hood, is just a bunch of weighted mathematical calculations. And essentially what we mean by those weights is basically just different numbers and tweaks you can make to the math equations until you get the output that you're expecting for a given input. Um, Basically AI in a nutshell for you. Um, so this is why I think we've touched on this before, but this is why AI hallucinates so confidently, because according to its calculations, what it's saying is absolutely 100% correct. Which, as we all know, is definitely not the case. But because, as far as the AI is concerned, what it's saying is correct, it says it very confidently. Um, and I guess same thing goes too with like image generation and video. Right now we're getting into like video generation too, but yeah. So the next kind of thing that really differs GPUs and CPUs is in terms of graphics. Now, like we mentioned, GPUs are fantastic at graphics and performing all of the mathematical operations in parallel that are required to have good graphics performance, hence their name, graphics processing units. Now, there are several big things when it comes to graphics performance, which makes the parallel natures of GPUs perfect for. The first one is physics. Now, anyone who has taken a physics course knows there is a ton of math involved to basically explain how the most basic things in the world work. How that ball fell at the speed it fell and then bounced to the height it bounced at. There's a ton of math that goes into calculating all of that. And calculating each individual position in time is its own calculation that you have to rerun. Also, and it's a similar thing, in video game graphics as well. Try if you want to model real world physics in your video games, you essentially have to be always performing these calculations in order to simulate the real world environment at whatever frame rate you're trying to achieve. And yeah, it's a lot. The other thing also is determining where and how 3D objects are supposed to be placed as well as moved on the two-dimensional plane that you're viewing inside the video game itself. So the GPU has to do all those calculations. So essentially what happens is the GPU takes like the model, which essentially gets converted into vertices, which then gets converted into triangles, and then the GPU has to perform a bunch of different kind of matrix math to determine where your character is or where the camera is pointing, and then based on where that viewpoint is in the scene, take those objects and kind of do the matrix multiplication in order to identify the correct point on the screen in which to place them. And then you, of course, add on top of that all the various shaders and textures that you put onto those objects. So, if this sounds like a lot of computation that has to go on, you are correct, which is why the GPU is so good at it because it has so many cores to do all these calculations in parallel that it can make pretty quick use of it. Now, an easy way to see this in action is if you've ever tried to play a video game on like just the CPU versus a dedicated GPU, the dedicated GPU in basically every situation is going to be a significantly better experience. Now, kind of going back to the matrix math part of it, there, like I said, there's a lot of matrix math that goes on taking the coordinates in kind of like the model space and kind of reflecting that into the space that the camera will show like in the video game itself. And if you've ever done matrix multiplication before, you know it is very tedious to do, but thankfully GPUs are designed very well to handle this and to handle this very efficiently, which is why, again, GPUs are so good at this. Be able to handle, all those calculations, in a very quick and successive manner. Um, so and yeah, so like I guess going back to the trying to run it on the CPU, I guess there is the caveat. Whereas if you're using a very modern CPU that has a more modern integrated GPU in it, because basically every modern CPU these days has some sort of integrated GPU inside of it. If you're using like a modern CPU, comparing that to a dedicated GPU from like 20 years ago, yeah, it might not be as big of a difference. But if you're using, a GPU from the same generation as the CPU, it's going to be a night and day difference compared to running things on the GPU versus the CPU. So that's kind of like computation where the GPU really shines, doing all those. Uh, but again, like we touched on, there's a lot of straight computation that has to go on when doing kind of like computer graphics and that kind of a thing, which is why GPUs are so good at it because it can, like I said, handle them in parallel. The next point is the memory and power consumption of the two. Now, if you've seen the latest power draw numbers from the latest NVIDIA chips, they are quite eye-watering. There are full-blown desktop builds that use less power collectively than some of the latest NVIDIA GPUs, and even AMD GPUs for that matter. GPUs, especially the big beefy ones, whether that's the ones used in data centers or whether that's the high end gaming ones, they suck down the juice. Now, like if you compare that especially to like, Apple Silicon devices, which are kind of known for their power efficiency, it's not even close. Like the amount of power that GPUs suck down is kind of mind-boggling. But that is a little bit disingenuous too, because there are GPUs out there that use less power than some CPUs. Like there are some CPUs out there, like if we exclude like the server CPUs, because those things can suck down like, hundreds of watts. But if we're talking about like desktop chips, like the high end desktop chips, I want to say can be like in the mid to low hundreds is kind of like what your high end like super performant desktop chip kind of typically is, at least from like Intel and AMD. But you can get graphics cards that, run on like 75 watts of power or less and will still perform pretty decently. Like the Tesla P4 that I touched on, that I used for that prime number factorization thing, that's just a 75-watt card. It only uses the power coming from the PCIe slot it's plugged into. And most of the time, it's like, because we touched on in the similarities between the GPUs and CPUs, it can idle down its like clock speed and frequency and basically kind of go into a sleep state of sorts, like a CPU can, in order to kind of reduce its power draw. So there are examples for sure where GPUs can use 75 watts. I've seen cards use as little as like 50 watts or maybe even like 35 watts. Obviously, those aren't going to be very performant, but you can find instances where GPUs aren't these power hungry monsters and suck down tons and tons of power. But typically speaking, when you're talking about high performance GPUs and high performance CPUs, the GPUs are always going to be drawing significantly more power than the CPUs are. But the other difference, kind of big difference between them is like the memory, how memory is handled between the two. Now, yes, if you're talking about like Apple Silicon, it's all unified memory, and that's kind of its own ball game. But on your typical kind of like desktop build, you obviously have your CPU with its system memory, and then you have your graphics card that has its own, video memory specifically for the GPU. Now, because GPUs are designed specifically for, processing large amounts of data, GPU memory is designed more for high bandwidth at kind of the cost of higher latency. So because GPUs are, designed specifically to process, large amounts of data, you want to have that high bandwidth to be able to reach into memory and grab out, the data you need in order to process as much as you can. And then, yeah, if it takes a little longer to load more data into memory, you already have a ton in there that you can, process in the meantime. And this is one thing that you'll notice while doing GPU programming, because if you aren't loading up that GPU with memory, you're going to notice that the CPU is probably actually quicker than the GPU is. Even though the GPU has all these cores and has all this power just waiting for it, if you aren't adequately using its memory properly, it's going to be faster to use the CPU. And this was evident, like I touched on in my uh, finding the prime factors program that I kind of said we're going to get back to. Well, we're getting back to it. So I mentioned the GPU is able to essentially smoke the CPU in terms of like the big, compute numbers. And the reason for that was how the algorithm worked was it would basically create a massive array of numbers, and then it would basically copy that data to the GPU, and the GPU would essentially go through in a sieve pattern and basically go up to the square root of whatever number it was trying to find. And then, if you're interested, you can kind of look up how like prime sieves work, but essentially that's what I was using. So you go up to like the square root of the number, and then you can basically cross out, the numbers, and eventually you'll find what the prime factors are. But obviously, if your number is very small, you're not going to be copying much data to the GPU. But the latency and kind of time it takes to copy that memory to the GPU is fairly is basically the same like amongst runs. So the thing that I was noticing was the CPU is absolutely creaming the GPU for like the smaller numbers because that overhead latency of copying all the data to the GPU, performing the very quick calculation and copying the data back took longer than what it took the CPU to just perform the quick calculation. Um, so but then of course when you got to like the much larger numbers, then that overhead kind of was significantly reduced because the CPU of course has to take a lot more time to process. So that's kind of you see a flip essentially happen where then the GPU kind of takes over to be the winner. And the reason why this was very evident was when you looked at the numbers between like all of the small, values, basically the numbers from say only having, I don't know, like 5 digits to say like having say 7 or 8 digits or maybe even 10 digits. I don't remember. There was a wide range of numbers that the time for the GPU to complete the computation was the same for all of them, which is a basically a red flag that you're dealing with a memory latency issue of there's more time is being taken to actually copy the data to and from the GPU than actually performing the calculation. Where that was not the case for the CPU. Essentially, every time you added, made the number larger, it took the CPU slightly longer and longer and longer to make the calculation. But that wasn't the case for the GPU. It was basically the same because of that, memory copying. And that's basically the work of, the latency versus the bandwidth type of thing that we touched on. So I guess to kind of put this in context a little bit, if none of that made sense to you, which if it didn't, I don't blame you, because it's not like I gave you any kind of graphs to look at to kind of really conceptualize this. But imagine you're in like it's say in a track meet and you're able to run a 100-meter dash in 12 seconds, and you know that all your competitors, the fastest they can run 100 meters is say 30 seconds. Obviously, you're going to smoke them every single time. But if when the gunshot goes off for you to start, if you have to put your shoes on, lace them up before you start running, it's a lot more of a level playing field, and you might actually the one be getting smoked, even though you're technically the faster runner, because that overhead and all that overhead you accrue by having to put your shoes on and lace them up before you can run gives the others a massive head start compared to you. And that's essentially what's kind of going on here between the CPU and GPU in this specific instance. All the overhead of copying the memory to the GPU reading that in, doing the calculation is the fast part. That's you running the 100 meters in essentially 12 seconds. But the part of you kind of having to put your shoes on and lace them up before you run is that overhead of you copying the memory to the GPU and then copying the result back and then, seeing the result. So that's kind of some of the big differences between CPUs and GPUs. But as far as future trends are concerned, I think what I mean, we're already seeing this. We're already kind of seeing a convergence of CPUs and GPUs. I mean, Apple Silicon is a fantastic example of this. Apple Silicon is essentially a single processor, an SoC, a system on chip, and it's basically including everything that's needed for the computer to operate all in that one package, right? It has the handlers for reading and writing data to SSDs. It has the neural processing units. It has I guess they call it the neural engine, excuse me. It has, the media encoders. It has GPU cores. It has CPU cores, all this good stuff. But also you look at like Intel CPUs as well. They've had quick sync for years now, which is essentially, media encoders. They have integrated GPUs on board. Now with the whole AI boom, they're getting like dedicated AI encoders in them as well. Apple has the neural engine. Intel has, I think, Gaudi, I think is what it's called. NVIDIA has their tensor cores. So you're kind of seeing kind of a convergence on both sides of CPUs trying to integrate these kind of AI and GPU features, and GPUs also trying to integrate kind of these AI features in order to speed up the processing. Because as we mentioned, if you can have hardware dedicated specifically to perform one task and perform it really well, it's going to not only reduce your power draw, but also improve your overall performance, which is obviously a very good thing. But I think that's kind of what we're gonna really start to see, which we've kind of already started to see. Um, but yeah, kind of like I also mentioned, we're seeing this kind of convergence of, CPUs with their integrated GPUs. But the other thing we're also it's going to be interesting to watch is the process shrinks are becoming less and less, I guess, major, right? Like, a few years ago, you were seeing process shrinks from, say, like, 22 nanometers down to like 14 nanometers, down to like 10 nanometers to 7 nanometers to 5. And now I think Apple went from like 5 to 3. And then the rumor is their next one's going to be down to 2. So obviously that's, still really, really small, obviously. But we're going to get to the point where you really can't shrink the transistor much anymore. So in order to kind of create you can't kind of get that initial like just easy easy speed improvement by shrinking the transistor size and adding more transistors to the same package, because that was kind of the, I guess, cheat code, if you will, of basically since the inception of the CPU, is if you can shrink the process size and put more transistors in the same package size, you get improvements in performance just through the shrink and the transistor size. But when we get to the point where you can't necessarily shrink the transistors anymore, really the only way you're going to be able to see improvements in performance is either through architectural changes with how the kind of the transistors are laid out and organized, and also the number of cores that you can have in order to perform things in parallel. Now, on the GPU side, that's not necessarily an issue because the whole point of GPU programming, essentially from the inception, is to do things in parallel. But that's not necessarily the case on the CPU side, because there are instances even today where some modern software cannot take advantage of all the cores on a CPU. Like, I'm trying to remember the exact test, but one of the benchmarks that YouTubers love to use when like testing CPU performance, I don't remember if it was like Cinebench or I want to say it was maybe Cinebench or Geekbench. I don't remember. It was some like CPU testing suite that they were using, like wasn't able to take advantage of all the cores on like some of these, monster server CPUs with like hundreds of cores on them. It just basically didn't know what to do with them. So unless there's software support to really take advantage of all the extra cores, it's going to be hard to see massive speed improvements. Now, obviously, if a CPU has more cores, even if programs aren't inherently very multi-threaded, it's still going to be able to run more programs at the same time because it has more cores. Now, of course, the operating system is going to have to manage that, which I don't have any doubt that operating systems will be able to handle that task. But suffice it to say, I think the number of cores on both CPUs and GPUs is going to continue to rise in the future upcoming years. But who knows? It'll be interesting to see. I mean, I don't necessarily like, if you look back, 5, 10 years ago, I don't think people would expect, we would be where we are today. So who knows what it's like in 5 to 10 years. But I think that's basically going to wrap it up. But before we close out, we have to get back to our trivia question, which is Skype, which was just discontinued by Microsoft this month, RIP, was initially released when? So when was Skype initially released? If you said 2003, congratulations, you got this week's trivia question correct. Specifically, it was the 29th of August in 2003. So if you're able to get that, I guess bonus points to you. But yeah, I guess Microsoft is like, let's get rid of Skype and force everyone to use Teams. Rip. Thankfully, I don't have to use Teams anymore, at least not at the moment, which I am very happy about, because I did have to use Teams in the past. And as far, I guess minor tangent here. I know we're kind of at the end of the episode, but when it comes to like video conferencing platforms, I'm not really a big fan of like any of them. Like Teams, I don't like Teams. Zoom, man. I don't know, like, the Zoom rubbed me the wrong way, like, when the pandemic first happened and, like, everyone was, like, using Zoom, and then there was, like, that massive, like, there was, like, a couple, like, massive security vulnerabilities that came out about Zoom, like, shortly after that, and then basically ever since then, I was like, "I don't wanna use this platform ever." And let's see what else. I think there's been, like, a couple others I've used. Honestly, the only one that I don't necessarily have any bad feelings towards per se is like FaceTime, which I know kind of makes me probably sound like an Apple shill, but I guess whatever. But even if you don't have an Apple device, you can still join FaceTime calls now, I guess, through the web. Sure, you can't create them, but you can join them. Um, but yeah, anyway, tangent aside, that was the trivia question. That's going to wrap it up for this week. So remember, if this question this week, the main topic came from a listener suggestion. So if you have any topics, ideas, questions for future episodes, or if you have any comments or questions about this week's episode, if you're on YouTube, leave a comment down below, or you can always shoot me an email if you're on podcast at contact@darkassassins.inc.com. Again, the link for that is down in the show notes below. And that's going to do it for me in this episode of the Dark Assassins podcast. Until next time, my fellow assassins, remember, bull nothing equals true. If action not equal to null, return true. I'll see you next time on the Dark Assassins podcast.